Hello everyone and welcome to another tutorial on vector in motion. Today we are going to discuss about internal forces in beams and in particular about shear forces and bending moments. Let's first check what kind of internal forces are present in two-force bodies. Here is a two-force body which is subjected to external forces at 2 points of the body, and when it is in equilibrium, the external forces have to be aligned with the longitudinal axis of the body. This is necessary for the equilibrium of this body. And now let's say we want to find out the internal forces at this point, and what we do, we cut the body into two parts, and by doing so we expose the internal forces at this point. Here in the next diagram you see the two separated parts, and these are the internal forces which get exposed. So these forces are called normal or axial forces because they are along the longitudinal axis of the body and they are normal to this face of the section, and therefore they are called normal forces. And in this particular case, when the external forces are directed away from the body, the internal forces also are directed away from the body, and therefore they are called tensile forces because they are stretching the part on which they are acting. And if the external forces on the body are just in opposite direction, like this, but aligned with the axis of the body, then the internal forces developed at the section are directed towards the body, like this or like this. And in this situation, they are squeezing the body on which they are acting, and therefore they are called compressive forces. So in short, when you have a two-force body, the internal forces are just the normal or axial forces. So the question arises, in what kind of a body you have shear forces and bending moments? So let's explore the situation in a multi-force body. Here we have a multi-force body such as a beam. The beam could be simply supported like shown here with multiple forces acting on this. This is a pin support, so this can be replaced by a vertical force acting like this. And similarly, this is a roller support, so it can be replaced by a vertical force. So we find that there are multiple external forces here in this case, and in the case of a cantilever beam, there would be reactions here and also a moment. And now let us examine what is the internal force at any point along the length of the beam. Suppose we want to find out the internal force at this point. So what we do, we cut the beam again like we did in the previous case, and we get two parts and we expose the internal forces. And now we find that from equilibrium considerations that this external force has to be nullified by a vertical force acting downwards, and this is what a shear force is. Similarly, the moment of this external force P about this point has to be nullified by a moment M opposing the moment caused by the force P in order to keep this part in equilibrium. So now we find that there is a shear force and there is a bending moment as internal reactions. And since this force is vertical and our beam is horizontal, there is no component of this force along the axis of the beam. So there is no normal force or there is no axial force. Typically, beams are subjected to vertical forces, and therefore we have only the shear forces and bending moments. Also notice one point, that in the case of two-force bodies, the normal or axial forces are same throughout the length of the body, but that is not the case here. The value of shear force and the bending moment would vary from place to place along the length of the beam. Here is a diagram showing the tiny shear forces spread all across the cross section of a beam which has been cut at, let's say, this point, and notice that the shear forces are tangent to the cross section of the beam. They are perpendicular to the longitudinal axis, and all these tiny forces acting at the entire area of the cross section, they add up to a single shear force that we show as a shear force in our free body diagram. The external forces acting like this also have an effect of bending the beam. For example, in this situation, when you have external forces acting downwards, the beam has a tendency to sag or bend with concavity upwards like this. And this bending of the beam, which is a little exaggerated in this diagram, but there is certainly some bending, and that causes stresses of another kind. Here in this diagram, you see the cut section of a beam. This is the cross section of the beam, and you find here forces of different magnitudes but parallel to the longitudinal axis of the beam acting at the cross section. There are some forces which are directed away from the face of the beam, and there are some which are directed towards the beam. These are tensile and these are compressive forces, and you also notice that their magnitude is largest at the upper surface, and as you go downwards there is a part of the cross section where there are no forces, and as you go further down you find that the direction has reversed and they have become tensile. This is so because when the beam gets bent like this, these are two arcs of a circle, and you notice that the upper surface has a smaller radius, the bottom surface has a larger radius. This length has got shortened and this length has got elongated, and there is a axis which is a neutral axis which remains the same in its length, same as what the original beam is. In other words, the upper surface has become compressed and the lower surface has become elongated. So in the compressed section we have compressive normal forces, and in the bottom section which is stretched we have tensile forces. But for each of the compressive force there is a corresponding tensile force, and therefore the net normal force along the axis is zero. So the point I am trying to make is that the net normal force is zero. However, these two kind of forces produce a moment like this, and this moment is represented in our free body diagram as a moment of the couple. To summarize, if the external forces are only vertical forces, then there are no normal forces. Nevertheless, the internal forces comprise of shear force, which is tangent to the cut surface, and there is a moment which is developed due to normal forces of different magnitude along the cross section of the beam. But there is no net normal force. Okay? Another important aspect is the sign convention of the shear forces and bending moments. When you cut a beam into two parts, you get the left part and the right part. The cut section of the left part will show shear force and a bending moment, and so is the case with the cut section of the right part. On the left part, the shear force is considered to be positive if it is pointing downwards, as you see here, and a counterclockwise moment is considered positive. The shear force acting at this face of the right part of the beam is considered positive if it is pointing upwards, and a clockwise moment is considered positive, and their sense is just the opposite. So it is better to remember the direction of the shear force and moment on the left part so that there is no confusion. Now I'll show you how to use the sign convention through a simple example. Here in this example, we have a simply supported beam which is 4 meters long, and the load consists of a single force at the midpoint of 10 kilonewtons. The pin support is replaced by a reaction force, and so is the case here at point B, which replaces a roller support. By taking moment of all the forces about point A and then at point B, we can easily work out that the reaction forces are of 5 kilonewtons magnitude, both at A and B. So we have in totality 3 forces acting on this beam, and our objective is to find shear stress and bending moment at all the points along the length of the beam. The load changes at points A, C, and B. So in order to determine shear force and bending moment in the region A to C, we choose any point which is at a distance of x from point A and draw free body diagram of the left part. So here is the ABD, and as you can see, there is a force, the reaction force acting at A, and at this end we had to apply the shear force and bending moment. We assume that the shear force and bending moment at this face are positive. That is, the shear force is pointing downwards and the moment is anti-clockwise. And next we write the equilibrium equations. Sigma Fy equal to 0 and sigma m at this point equal to 0. And we stick to our usual sign conventions, that is, the forces pointing upwards are positive and anti-clockwise moments are positive. These sign conventions are up to us, but this sign convention of the bending moment and shear force is as per this sign convention, and we do not have any freedom to change this. Summing the forces in y direction gives us 5 minus v equal to 0, and that gives us v equal to 5. And taking the moment of all the forces about this point gives us minus 5 times x plus m1 equal to 0, and m1 turns out to be 5x. That is, both these values are positive, and therefore we can conclude that in reality the direction of the shear force and the bending moment are same as what has been shown here. That is, they are positive. And when we draw the shear force diagram, we show positive value of 5 kilonewtons between A and C, and this is the oblique straight line representing m is equal to 5x. Next, to determine the shear force and bending moments between points C and B, we choose any point and give an imaginary cut. The point at which we cut is at a distance again x from point A, and we pick up the left part and draw its free body diagram, which you can see here. And again at this end we apply the shear force and bending moment, and we assume that they are positive, And again we apply the equations, the equilibrium equations, sigma F5 equal to 0 and sigma M2 at this point equal to 0. Our sign convention for these two equations would again be the same. That is, upward forces would be positive and counterclockwise moments would be also positive. So 5 minus 10 minus V2 will be equal to 0, and that gives us the shear force is minus 5. So between the 2 points C and B, the shear force is negative. And again we take moment about this point of all the forces, and we find that minus 5 times x, because this causes clockwise moment, this causes anti-clockwise moment, so 10 times x minus 2, this term here, plus m2 equal to 0, and that gives m2 equal to minus 5x plus 20. And we notice that for any value of x between 2 meters and 4 meters, this will be positive. So this is the line representing this equation. So in both regions A to C or C to B, bending moment is positive. However, as far as shear force goes, between A to C this is positive, and between C and B it is negative. Okay? There is an alternative way of remembering the sign convention for shear force and bending moment. In this approach, the focus is entirely on the external forces, and as per this convention, the shear force at this point is considered positive if the force on the left part has a tendency to shear off this part as indicated here. In other words, if the forces on the left part are acting upwards, it would mean the shear force at this point is positive. And the shear force as shown here in this diagram would be considered negative if the forces on this part, the left part, shear off the left part in this direction relative to the right part as indicated here. Similarly, the bending moment at this point is considered positive when the external forces tend to bend the beam with concavity upwards as shown here, and if the external forces tend to bend the beam as shown here with concavity downwards, then the bending moment here is considered negative. So let us apply these sign convention relating to external forces and work out a simple problem. What I just explained can be understood from these two equations. We take the same example, and let's say we want to find shear force and bending moment at this point. So we examine the forces acting on the left of this point. And what this first equation says is that all upward acting forces would be positive and all downward acting forces would be negative. And the sum of these two will determine the sign of the shear force at this point. If the total of this turns out to be positive, that would mean a positive shear force at this point. If it turns out to be negative, then it would mean a negative shear force at this point. So in this particular case, we see that there is a single force to the left of this point, and that is pointing upwards. So from this equation, we can conclude that shear force at this point is positive. And that would be the case for any point between points A and C. So our shear force diagram will show a positive value between point A and C. Now let us take up another point which is to the right of point C. Let's say this point. And to apply these equations, we examine all the forces acting to the left of this point. And now what we notice is there is one force which is acting in positive direction, and that value is 5, and the value of the other force is minus 10 because it's pointing downwards. So the net force is minus 5, and therefore the shear force would be minus 5 at this point. So between points C and B, the shear force would be minus 5 kilonewtons, as you see here in this diagram. Let us take up the second equation, and what it says is that all clockwise moments to the left of this point would be positive, and all anti-clockwise moment or counterclockwise moments would be considered negative. That is, upward directed forces would cause clockwise movement, and all downward forces would cause anti-clockwise movement and will be considered as negative. So let us see at this point what will be the bending moment, and we find that there is a single force pointing upwards and it will cause clockwise movement. So the bending moment here would be positive, as can be seen from this diagram, and this equation gives the same meaning. Let us consider this point. Here the bending moment will be equal to 5 times this distance minus 10 times this distance. This is minus because it's pointing downwards and will cause a counterclockwise movement. So in this sign convention, all upward directed forces would cause clockwise movement and will be considered positive. All downward forces to the left of this point will cause anti-clockwise moment and will be considered negative. So at this point we have 5x and 10 times x minus 2 is the distance here, and this will be negative, this term here, and this works out to minus 5x plus 20, and for any value of x between C and B, the total value of m would be positive. So we will have positive bending moment. So we find that the result is the same as we got in the previous method. This is a simple alternate way of remembering the sign convention, right? I would also like to add that from the equilibrium equations we can draw these two diagrams. Another approach is a graphical approach in which we do not write all these equations, but we can straight away plot the curves, and in that process this convention, the second convention that I talked about, will be quite handy, right? So I hope you found this useful, and in the next few videos I'll be solving some problems employing both the methodologies. So thanks for watching and see you in the next video.